There are so many things that move around us. The wind blows, birds fly, trains run on tracks, there are cars on the road, and you can see that there's motion everywhere. But understanding the nature of motion has taken humanity a very long time. In fact, until 400 years ago, people used to think that a body moves, or rather keeps moving, only if there's something pushing at it. So if you were to stop that thing from pushing, it would come to a rest. Now, Aristotle, who was a very wise man, had a theory of motion which today you and I might find a little peculiar. He said that a rock will fall to the earth because that rock is a part of Mother Earth, and Mother Earth is pulling it downwards. Take an arrow, he said. An arrow needs a push from the bowstring, or a spear needs to be thrown. But then what keeps it moving? Well, he said, as the spear moves forward, the air rushes behind and so keeps pushing at it. Well, what about the planets in the sky? And people used to think that, well, there's got to be something pushing at the planets. And so it has to be angels, or it has to be some kind of supernatural creatures. But that was a long time ago. And then came the modern age with Galileo and Newton. And today we have a very different view of motion. What causes it, what sustains it. And that is something that you and I are going to talk about today. But we won't just talk, we will use the ideas that are developed to actually do a few experiments and know that what we are doing is indeed sensible. So today, I want to introduce some basic concepts. Well, first of all, I want to talk about mass. Well, mass is really a measure of the quantity of matter. So if I have a ball, well, this ball is matter, and this ball has a certain mass. If I had a bigger ball, it would be something with a bigger mass. All right, so mass is clear. Now there's another thing, and that is momentum. Momentum is like a measure of motion, and it's a product of two factors. First of all, mass, which I'm going to call m, times the velocity at which that mass is moving. So if this ball is moving faster, its velocity is greater, and the momentum is correspondingly greater. That's if it was moving this way. But if it's moving backwards, well, then it will be mass times minus v, and so the momentum is going to be backward. All right, so you could say momentum is a measure of the amount of motion that you have. So that's clear. Now we go on to another concept, and that is of kinetic energy. And that is half m times v or half mv squared. Kinetic energy, the word kinetic comes from the Greek kinesis, which means motion. So you could say that this is motional energy. All right, so these are two new concepts that you've learned today. There's momentum and there's kinetic energy. Before we break, I want to ask you a question. Suppose there's a motorcycle and a truck, and the truck weighs 100 times more than the motorcycle. If they both have the same amount of momentum, how much kinetic energy will the motorcycle have in comparison to the truck? So when we come back, I'll expect you to have the answer. You will remember that I made two definitions, one of momentum and the other of kinetic energy. But what use are definitions unless one uses them? The use of the definition of momentum comes really from Newton's first law, which says that if you have a body that's far away from every other body, then its momentum remains constant. Now, the real use of this comes from the fact that it just doesn't have to be one body alone. But suppose you have a whole bunch of bodies. You have 2 bodies or 3 bodies or 20 bodies, but these are all somehow far away from everything else. Well, the total momentum of this collection of bodies is going to be a constant, provided this collection of bodies is far away from every other set of bodies. Okay, that is called the conservation of momentum. The reason I talked about kinetic energy is because kinetic energy is another form of energy. As you know, there is heat energy, chemical energy, electrical energy, and so forth. And all of these energies are able to convert from one form into the other. Now, kinetic energy will be conserved if two bodies collide with each other, provided that it's a special kind of collision. And now let me come to the subject of collisions, which we're going to talk a lot more about during this lecture. So, let's say that I have one cricket ball and another cricket ball. Okay, when they collide like this, well, this ball doesn't really lose its shape. It remains as it was. And so you have a situation where kinetic energy is more or less conserved. So what you see is that this ball and this ball, after they've collided, they have kept moving. And if it is a perfectly elastic collision, then the kinetic energy before the collision and after the collision are exactly the same. That will happen when nothing happens to the balls. So you could define an elastic collision or a perfectly elastic collision in which nothing happens to the objects that collide with each other. On the other hand, if I have two eggs and these two eggs collide with each other, well, if they collide hard enough, they're not going to remain in their present form, and kinetic energy will not be conserved. Well, let's see. So here's the ball that I'm going to drop. It dropped, and okay, nothing very much happened to it. Of course, the energy was lost in various forms because you heard that sound, so some of the energy was given off in the form of sound, but most of the energy remained in the form of kinetic energy. On the other hand, look at this egg. As I drop it, it broke. So this was a highly inelastic collision. Now, let's come to this issue. Under what circumstances is a collision elastic, and under what circumstances is it inelastic? So before we come to the break, I want to ask you this question, that does the degree of elasticity of a collision depend upon the speed at which bodies collide with each other? Think about that. And there's another question I want to ask. Can you think of any situation or any system where you have a perfectly elastic collision? And again, I repeat, an elastic collision is where the initial kinetic energy and the final kinetic energy are exactly the same. And an inelastic collision is one in which they are not the same. So kinetic energy is lost. Of course, that doesn't mean that the energy has been lost or has gone missing. It just means that it's turned into another form. So when we return, we're going to use the fact that certain collisions can be very elastic, and then we'll use that to go further. Let us apply the two laws that we've learned, namely the law of conservation of momentum and the law of conservation of energy, to a slightly different situation. So what I want to consider as a new situation is the mass m moving with velocity v. It hits the mass m which is at rest, and then after the collision, the first one moves off with velocity v1 and the second with velocity v2. Now, I don't know what v1 and v2 are, but the law of conservation of momentum and of energy are going to tell us what they are. So let's apply them. First, the initial momentum, that is to say the momentum before the collision, was mv, and the momentum after the collision is mv1 plus mv2, or we can cancel the m and get v equals v1 plus v2. Now let's apply the conservation of energy. So half mv squared is half mv1 squared plus half mv2 squared. And again, we can cancel the m's. We get v squared is equal to v1 squared plus v2 squared. So we've got to solve this equation and this equation. How do we do that? Well, let's square the first one. That way we get v squared, and then equate it to this v squared. So v1 squared plus v2 squared is equal to v1 squared plus 2v1 v2 plus v2 squared. And now I can cancel this and this with this and this. And that gives us v1 into v2 is 0. Now there are three possible solutions of this. v1 and v2 can both be 0, but that doesn't make much sense, because you wouldn't be able to then satisfy this equation. You'd have v over here and 0 plus 0, which is not right. Then we can have v1 as 0 and v2 as non-zero. And let's see what v2 has to be. Well, it's clear that if v1 is 0, then v2 has to be v. The solution over here, v1 equals 0, v2 equals v, obviously satisfies this. And what this is saying is that the first body comes to a stop, 0 speed, and the second body moves off with the speed v, that is the initial one. So now let's go out and try and see if this is actually the case. And now the only thing that we have to do is go back over here, and now this is going to come and strike this with speed v, and if what I've said is right, then this one comes to a rest, and this one moves off with the same speed that this hit it with. Okay, let's go. That's exactly what we expected. That's what happened. And one more time. When we come back after the break, you're going to see not 2, but 3, 4, and 5 balls. So ask yourself, what will happen in that case? So I want you to predict, on the basis of what we have learned right now, what will happen when there's a third ball, a fourth ball, and a fifth ball, and this first ball comes and strikes this one. Let's see if you can guess the answer by the time we come back. As we predicted earlier, if one ball comes and strikes another ball, and if the collision is elastic, then the first ball comes to a stop and the other one starts moving off with the same speed as the first ball. This is what we saw over here, that the solution is v1 is 0 and v2 is v. All right, now let's see what happens when there's a third ball that's involved. So I'm going to move these two away from the scene. And here is going to come the first ball, hit the first one, or rather the second, and that hits the third. And now that's exactly what we'd expected, right? That the first one communicates the energy and momentum to the second, which then communicates to the third. Let's repeat with now 4 balls. and see how that works out. Okay, so you get the idea there. And now let's try for 5. Here's 5. Now, there's one last thing before we go on to something else, and that's what if two balls are coming together, one from this side and the other from this side. Let's see what that does. Of course, this could go on forever. It's a very amusing plaything. But basically, it's just one ball hitting another, and we're just using what we've learned over here again and again. But now I want to come to something slightly different. What I'm going to do is ask you to complete a calculation that I'm just about to start. And so in here is a mass, m, which comes in with speed v, but now it's going to hit something that's twice as massive, so it's got mass 2m, and I want to find out what happens after the collision. And so I'll set up the equations and you solve them. So the initial momentum is m into v, so m into v plus 2m into 0, okay, that's 0. That is equal to the final momentum. So you see the final momentum of this one is, we're going to call it v1 as before, and the final momentum of this one is going to be mv2, so velocity v2. Conservation of momentum reads mv is equal to mv1 plus 2mv2, and conservation of energy reads half mv squared is half mv1 squared plus half into 2m v2 squared. And so these two equations are just v equals v1 plus 2v2, and the second one is v squared is v1 squared plus 2v2 squared. Again, you can solve this as I did before, but you're going to do it and I'll give you the answer. The answer is that v2 is 2/3 of v, and v1 is minus 1/3 of v. So check this out, but look at what this is saying. This is saying that the first ball is going to, so the one that strikes the big one is going to recoil at speed minus 1/3 v. The final speed, that is of the 2m, is going to be 2/3 v. Actually, you can check very easily that this satisfies this. Just put this in here. So that's minus 1/3 plus 4/3. That satisfies, and so forth. Now, this is saying that there is recoil, but you see, it's in that direction, and this is going off with speed less than the speed with which it was hit. So the heavier body has absorbed some of the momentum and energy of the lighter one. Not all of it, but at least some of it. Based on this example, I'm going to ask you a question. So I have over here a little ball that I'm going to drop to the floor, and you see that it drops and comes back. When it hit the floor, it was moving downwards, and when it rebounded, it was moving upwards. So obviously there's been a change of momentum. Change of momentum, well, that means momentum is not conserved. That's my question. Now, similarly, if I throw it against a wall, again, I see a change in momentum. It was moving this way, then it went that way. So what's going on over here? Think about this during the break. I hope you had time to reflect on the question that I had asked you before the break, because it's a very important question. To remind you, it was this situation where I drop a ball and the ball strikes the ground, comes up. Apparently, there is no conservation of momentum. But why? Well, the reason is that, yes, this ball's momentum has changed, but so has the momentum of the earth. When this ball struck the earth was forced down. It absorbed the momentum. It gained momentum as a consequence of the ball striking it. Now, that sounds a little strange, doesn't it? I mean, the earth is so big. How could a tiny little ball like this change the momentum of the earth? But that is exactly it. The total momentum, which means the sum of the momenta of the ball plus the earth, doesn't change. Okay. Still, it is a fact that the momentum of this ball changed. And Newton's law says that the rate of change of momentum, delta P by delta T, is the force that acts on a body. So, saying this in different words, if the momentum of a body changes by amount delta P in time delta T, well, that is because a force F has acted upon it. Now, let me use this to explain something that is of very common knowledge, and I'm sure will be of interest and of use to you if you're a cricket player. But before that, let me write this as delta P is equal to F into delta T. Again, what this means is that if a force F acts for a time delta T, that causes a change of momentum, which is delta P. Now, note one thing. F can be large and delta T can be small to give delta P, or F can be small and delta T can be large. That gives the same delta P. So now let's come to the question of the cricket ball. As any good fielder knows, if this is a ball that's coming towards you and you have to catch it in this hand, well, you're going to let the hand go back a little bit. In other words, delta T is allowed to be longer so that the force is smaller. Of course, it leads to the same change in momentum, that change of momentum being whatever it was initially to zero. Zero because the ball has to come to a stop. So, if you move your hand backwards, you allow a larger time and hence a smaller force. Now, a smaller force hurts your hand less. Let's take another example of this. Now, you remember that I had dropped an egg on this table and the egg broke. I'm not going to do that again. But let's take a softer surface. Okay, I'm going to drop it from pretty much the same height, and the egg didn't break. Why not? Well, exactly the same reason. The reason was that a smaller force acted for a larger time, and that gave the same change in momentum, that is, the initial momentum minus the final momentum being zero because it came to a stop. Hence, what we see is that this egg did not break. We had, nearly an elastic collision. There is a lot more that we can talk about, but we've run out of time. All I'm going to say is that Newton's laws are so fundamental to physics and so fundamental to having created the world around us that, practically nothing in this world would be in the shape that it is if it wasn't for our having understood the mystery of motion. Now, Newton's laws require critically the definition of momentum. And so let's go back to that just very briefly. You remember that I had defined momentum P as the mass of the body into the velocity. And then, of course, rate of change of momentum is the force. Is it true that this holds all the time, everywhere, and in any situation? And my answer to that is, it's 99.99% true, but it's not 100% true. I say 99.999, etc., because look, of all the things that we see around us, we see cars or rockets or planes or whatever, they're not moving close to the speed of light. But what Einstein showed, and this was in 1905, it's more than 100 years ago, was that if some bodies start moving close to the speed of light, for example, electrons, well, this formula over here doesn't work. It has to be modified, and it's only a tiny modification. All you do is multiply this thing by a certain factor. It's called the gamma factor, but I'm not going to talk about the gamma factor. Think of this as 1 for all practical purposes here on Earth. But when you go to the subatomic world, to atoms, to electrons, this gamma can be very large. This is the difference that can lead to nuclear energy, that can lead to us understanding how the stars shine, where they get their energy from, their light from. But that's another story. That's all for today. I hope that you've understood some of the basic concepts that we introduced. Of course, there's a whole lot more. These remarks are only meant for teachers. I hope you enjoyed this program. There are lots of other things that you can do with your students. Of course, all the material that you saw, you can find in any decent textbook in physics. Basically, it's just mechanics. The sort of extensions that you can look at are, for example, applying the conservation of momentum to 2 dimensions and then to 3 dimensions. 2 dimensions or 3 dimensions, basically you've got to conserve momentum in each one of those dimensions. Let me come to the 2 questions which are, I think, a little thought-provoking. The first is, does it matter how hard you collide 2 bodies in terms of the collision being elastic or inelastic? The answer is yes. Suppose I take 2 steel balls, okay, and they collide at a reasonable velocity. Well, they bounce back with almost that same velocity, so it's an almost elastic collision. But now imagine that I was to throw those steel balls at each other with some huge velocity. If it was absolutely huge, the balls would just disintegrate. Even the iron, even the steel would break apart. So obviously there is a limit upon the speed at which you can throw these 2 balls together and expect them to remain the same. So elastic, yes, but always up to a point. Which then brings us to the next question. Is there such a thing as a perfectly elastic collision anywhere in the world? And the answer is yes. If you look at something that's absolutely impossible to change, something that is a fundamental particle, like an electron or perhaps a quark. But let's talk about electrons. Take 2 electrons, strike them together as hard as you like. Well, they're going to remain electrons. Nothing's going to happen. And so that's an example of an absolutely perfectly elastic collision. Finally, I'll say that if you take a gas, that gas has got lots of atoms and molecules, and they're all colliding with each other. So one goes and strikes the other. And there is no loss of energy because those are elastic collisions. So that gas is not losing its energy. It's just that the energy of one atom or one molecule gets transferred to the other, which gets transferred to the other, and so forth. So the subject of collisions is really very important to physics, not just in terms of, let's say, cars colliding with each other, although that's a good example to use in your classes, but also in terms of what goes on inside gases, inside solids, and inside all of matter. That's why when physicists study, when they begin to study physics, the first thing they study is mechanics. Mechanics is absolutely fundamental, and I hope you have a good time teaching that to your students.